Operational quantum gravity for engineers, a revised damping, vacuum polarizability, and uncertainty-based interpretation of gravitational scaling by Todd J. DiCiotto, Statesville, North Carolina, USA. Version 11 final, April 11th, 2026. Practically speaking, time is what clocks measure and space is what rulers measure. In this paper, I restate and consolidate my long-running program in the strongest form I believe can be defended rigorously from my manuscript series and the primary literature on which it builds. My central claim is interpretive rather than iconoclastic. Wherever the same field relations and scaling laws are recovered, the model makes the same observable predictions as general relativity, but it assigns a different physical meaning to those relations. In the present reading, the metric is a compact mathematical encoding of comparisons among physical clocks, rulers, signals, frequencies, and energies. It need not be taken as proof that a space-time manifold is the unique fundamental ontology. I summarize the static, weak field transformations of the Schwarzschild and polarizable vacuum representation and show that the adopted scaling preserves the Heisenberg products delta x delta p and delta t delta e exactly. I then write my radiative damping model in a form that reproduces the same transformation table through the identification k equals 1 over 1 minus zeta squared. The controlling quantity is treated as a real, effective scalar order parameter built from the local stochastic electromagnetic and magnetic environment seen by matter, and I add a phenomenological weak field source law together with a linear response bridge from the spectral environment to the damping variable zeta. The paper also states explicitly how universality of free fall can emerge at leading order when the K-map is common to all matter processes, and it sharpens the experimental program in precision spectroscopy, clock comparison, and resonance-based perturbation studies. Thermodynamic analogies are used as motivation, not as proof. The resulting synthesis is not claimed as a completed microscopic theory of gravitation. It is offered as a mathematically coherent operational interpretation of the same observed weak and static relations, together with a more explicit engineering research program for testing whether a deeper non-geometrical layer exists. Practically speaking, a clock compares rates and a ruler compares lengths. The quantities that enter gravitation are therefore operational comparisons among physical processes, not substances called time and space. General relativity encodes those comparisons in a metric, and I do not dispute its empirical success. My question is narrower. Can the same observational content be written in a more direct engineering language based on matter, vacuum response, damping, and scale setting processes? My manuscript series from 2006 through 2023 follows one line of development. First, the weak and static transformations associated with the Schwarzschild solution can be expressed through a single scalar quantity k in a polarizable vacuum representation. Second, the same table of transformations can be written so that the Heisenberg products remain invariant. Third, the same table can be matched again by introducing a damping factor zeta for matter treated as a driven oscillator in stochastic equilibrium with its environment. The strongest version of the program is therefore not that geometry is wrong, but that geometry may be descriptive rather than ontologically unique. That distinction matters. If the metric is descriptive rather than ontologically unique, then a deeper engineering model should begin with observables and then ask what microscopic changes in matter would cause the observed changes in clock rates, characteristic frequencies, lengths, and energies. My interpretive move is operational. Time is what clocks measure. Length is what rulers measure. The metric is a concise bookkeeping device for those relations. and a deeper causal layer may be sought in how matter is driven, damped, and scaled by its local environment. Stated plainly, I am not arguing that general relativity is empirically wrong in the regime treated here. Wherever the same field relations and scaling laws are recovered, the observable content of my model is identical to that of GR. What changes is the ontology attributed to the equations. As an interpretation of the same successful weak and static relations, I regard the present model as standing on equal empirical footing with the standard geometrical reading so long as both recover the same observational table. On this reading, Einstein's field equation may be approached operationally before it is approached ontologically. The geometric side summarizes the relational structure inferred from clock comparisons, ruler comparisons, signal propagation, and material motion. The matter side describes the stress energy content of the matter fields from which those same clocks, rulers, and signals are physically built. In that sense, the equation need not be read first as a declaration that a space-time manifold is the fundamental substance of nature. It may instead be read as a comparison law linking observed relational structure to the matter sector that sets the standards of observation itself. I do not regard the geometrical interpretation as a mistake in any simple sense. It has enriched the mathematics of gravitation enormously. My narrower concern is that its ontological primacy may also have constrained the search for quantum gravity by encouraging us to treat geometry as fundamental rather than emergent. One advantage of the present interpretation is economy. It keeps the successful mathematics where it works, but asks first what clocks do, what rulers do, and how quantum matter sets their scales. The polarizable vacuum line of thought runs from Wilson and Dickey to Puthoff's variable K representation of static gravitational effects. In that representation, the vacuum is treated as an effective medium whose single scalar parameter K summarizes how clocks, rods, and the coordinate speed of light compare between an altered region and a distant unaltered one. For my purposes, this is attractive because it preserves the observational content while replacing purely geometrical language with a form more natural to engineering analysis. In this paper, I adopt the same static line element in the spirit of my earlier papers. I do not present it as a new derivation of general relativity. I present it as the operational encoding of the same weak and static gravitational scaling relations that I wish to reinterpret microscopically. The point of the operational ladder is interpretive rather than decorative. The macroscopic metric coefficients, the polarizable vacuum refractive index variable K, and the microscopic damping picture are treated here as different encodings of the same observed weak and static comparison rules. In that restricted sense, the present model is a reinterpretation of the GR table, not a competing table. Once I adopt the operational statements that lengths are contracted and clocks are slowed in the chosen coordinate comparison, the uncertainty products must still be respected. This is the key point. The uncertainty principle constrains products, not isolated variables. The mathematical question is therefore whether one can choose the complementary scalings of momentum and energy so that the products delta x delta p and delta t delta e remain unchanged while the observable table of gravitational scalings is reproduced. One can. The proof is immediate by multiplication. This does not by itself derive the full gravitational field equations. It does something more modest and more secure. It shows that the scaling map I adopt is compatible with the kinematical quantum constraints. In that sense, the uncertainty principle enters here as a consistency condition on the scaling table rather than as a standalone first principles derivation of gravity. An important consequence follows if one further demands that force remain invariant in the adopted comparison scheme, then the quantity that scales like mass cannot be treated naively. What emerges is an effective coordinate mass parameter, I keep that point explicit to avoid the common misunderstanding that I am claiming the local invariant rest mass of a particle changes in its own local inertial frame. My claim is weaker and cleaner. Within the distant observer bookkeeping used here, an effective mass parameter must scale as k to the 3 halves power if the rest of the table is to remain internally consistent. In my later manuscripts, I move from a purely kinematic table to a microscopic picture in which matter is treated, for engineering purposes, as an ensemble of oscillators. In that picture, the quantum vacuum supplies a baseline driving field, while radiative damping and local environmental loading alter the steady state equilibrium. This move is motivated by the literature on vacuum fluctuation physics and by equilibrium accounts of radiationless quantum ground states. It is also motivated by the fact that oscillators provide a natural language for frequency, line width power flow, and resonance. The central equation is the driven damped oscillator. From it, I introduce the dimensionless damping factor zeta equal to gamma over omega naught, and the underdamped frequency, omega sub zeta, equal to omega naught times the square root of 1 minus zeta squared. In my engineering model, the reduction in available driving power and the shift in characteristic energy are then mapped onto the same table of gravitational observables. The model does not merely borrow the standard undamped harmonic oscillator ground state. It introduces a phenomenological fluctuation map in which the mean square position, velocity, and acceleration fluctuations scale with powers of 1 minus zeta squared. That is the step that allows the damping picture to reproduce the same operational relations that K already encodes. The identification K equals 1 over 1 minus zeta squared is therefore the hinge of the synthesis. Once that substitution is made, the frequency, energy, velocity, acceleration, and effective mass entries of the damping table collapse onto the same operational relations as the metric and polarizable vacuum table. That is the strongest mathematical equivalence in the framework. What remains open is the microscopic origin of zeta and the exact field theory behind it. It is also useful to say explicitly that the stochastic and spectral pictures of the vacuum are not competing ontologies. A stochastic field can always be described by its spectrum, and a weighted spectral density is one natural coarse graining of a random background. My present damping language therefore extends, rather than rejects, the earlier vacuum equilibrium language, in which particle scale was associated with equilibrium against a structured vacuum spectrum. In the older EGM harmonic work, the harmonic cutoff was interpreted as indicating the energy density at which matter reaches equilibrium with the surrounding polarizable vacuum and zero-point field. I do not present that as a proof of the current model. I cite it because it captures the same physical intuition that motivates the present one. Matter scale is not arbitrary, but is set by its equilibrium with a structured vacuum environment. In earlier drafts, I used the phrase Maxwell temporal field as a heuristic label. Here I make the intended meaning explicit. The controlling quantity is treated as a real effective scalar order parameter or coarse-grained state variable built from the local stochastic electromagnetic and magnetic environment seen by matter. This is the formulation most faithful to what I am actually proposing. I do not deny the baseline zero-point field of QED. My claim is that the actual environment experienced by matter is not an idealized empty baseline. It is loaded by surrounding matter, radiation, and internal hadronic and electronic activity. The local state, seen by an atom or nucleus, is therefore a real spectral environment, not a mere notational convenience. In this paper, I represent the control variable as a functional of that environment. I retain the language of scalar magnetic flux only as engineering shorthand for the magnetic sector of that stochastic environment. What matters here is the weaker and more defensible statement. Matter couples to a local stochastic field environment with a scalar control parameter capable, in principle, of shifting equilibrium frequency, available power, and fluctuation scale. That statement is sufficient for the present synthesis. It is equally important to say that the local stochastic vacuum and the local spectral vacuum are, in this framework, two ways of describing the same underlying physical layer. The stochastic description emphasizes loading, fluctuation amplitude, and local field variability. The spectral description emphasizes how that same environment is distributed in frequency. The present paper uses the stochastic language more often because it is better suited to damping, line width, response, and control, but I do not regard the two descriptions as physically separate. Point is that the stochastic background is not the same thing as the damping variable. The local spectrum is the environment. Zeta is the coarse-grained dissipative response of matter to that environment. Near equilibrium, it is natural to summarize the environment by a weighted spectral density and to summarize the response by an effective damping rate. I therefore introduce the auxiliary quantities environmental energy density and effective damping rate as phenomenological state variables, not as a completed microscopic derivation. Here, the weighting and response kernels encode which portion of the local spectral environment is relevant to the mode under consideration. This formulation makes explicit what is only implicit in my earlier papers. The environment sets both fluctuation amplitude and dissipative response, while zeta is the scalar summary that enters the operational K-map. In the absence of a completed microscopic field theory, I adopt a phenomenological weak field closure. The minimal requirement is that the source law reduce to the ordinary Newtonian potential for static spherical matter while still allowing the environmental language of the present model. I therefore define a weak field potential associated with zeta and take the effective source to include both matter distribution and environmental loading. These equations are not yet a finished microscopic theory. They are the minimal closure that connects matter distribution to the scalar control variable in the weak and static limit. For a point or spherically symmetric source, they reduce to the same leading order dependence used later in the paper. The baseline zero-point field drops out of the source term. What matters is the local departure from the unperturbed environment together with the matter distribution that generates it. Here I want to state more clearly how the equivalence principle enters the model. In the unperturbed state, matter is treated as residing in local radiative equilibrium with its environment. The equilibrium scale is set by a stationarity condition on the full matter plus environment system. Mean input power from the local field environment is balanced by mean radiative and dissipative output power of the bound system. I regard this local stationarity, not geometry by itself, as the symmetry relevant to scale setting. Stated carefully, the corresponding Noether statement belongs to the underlying closed matter plus environment system rather than to the reduced damped subsystem alone. The present paper therefore does not claim a formal Noether derivation at the coarse-grained level. It claims the weaker point that free fall can be interpreted as a gradient-driven departure from a locally stationary equilibrium scale. For the radiation reaction side of that story, the most appropriate benchmark is not the original Abraham-Lorentz equation, but the reduced order Landau-Lifshitz form, which avoids the familiar runaway and pre-acceleration pathologies of the Abraham-Lorentz and Lorentz-Abraham-Dirac hierarchy while preserving the leading radiation reaction content. Conceptually, this is close to the Ford-O'Connell perspective, in which radiation reaction is written in a way that is naturally compatible with open system and Langevin descriptions of a charge interacting with a bath. That viewpoint is especially congenial here because my model already treats matter as an oscillator embedded in a stochastic environment. The point is not that radiation reaction alone proves gravity. The point is that it provides the right structural lesson. Inertial response, dissipative response, and scale setting are all linked through the way matter exchanges power with its surroundings. If the coarse-grained response of ordinary matter collapses to a common scalar control field K or zeta, then leading order free fall is universal because the local acceleration is determined by the gradient of the equilibrium state rather than by a material specific force coefficient. Free fall is then interpreted as a tiny contraction in the equilibrium scale of matter as it moves down a gradient in the zeta associated potential. What is ordinarily called gravitational potential energy is represented in this reading as a change in the internal equilibrium state of atoms and particles rather than as a localized substance of spacetime itself. The non-trivial requirement, of course, is universality. Any material dependence hidden in the response kernels must coarse grain away to within Eötvös type experimental bounds. That is why the equivalence principle is not assumed here as magic, but treated as a constraint that any successful microscopic completion must satisfy. First proposition, the operational scaling map is compatible with the Heisenberg products. Choose the length and time scalings from the adopted K-table. Then choose the complementary momentum and energy scalings so that the products remain unchanged. Direct multiplication gives the result. No further assumptions are required. Second proposition, the damping map reproduces the operational K-table if K equals 1 over 1 minus zeta squared. Substitute the defining relation for K into the damping relations. The frequency and energy rhos immediately reproduce the 1 over square root of K behavior, while the velocity, power, and acceleration rhos reproduce the 1 over K and 1 over K to the 3 halves behavior shown in the unified scaling map. The effective coordinate mass parameter follows as the reciprocal power needed to preserve the force rho. The linear response definitions do not alter this algebraic matching. They only supply a more explicit interpretation of the control variable. Third proposition, in the static spherical weak field limit, the choice zeta squared of r equals 2 gm over c naught squared r, or equivalently the weak field closure with a point mass source, reproduces the usual leading order potential dependence of the K-table. Substitute that relation into the damping to K identification and expand for 2 gm over c naught squared r much less than 1. The leading order result follows directly. The Earth surface values are then obtained by numerical substitution of Earth's mass and Earth's radius. Fourth proposition, if K of x, or equivalently zeta of x, acts as a common scalar scaling field for all matter processes, then the leading order free-fall response is composition independent. In the weak field closure, the acceleration field contains no test mass parameter. Composition dependence can therefore enter only through higher order material response corrections hidden in the kernels defining zeta of x. The corresponding EOTVOS parameter must then remain below existing bounds. These propositions do not complete a microscopic theory of gravity. What they establish is an internally coherent ladder of equivalences: metric scaling, K-scaling, uncertainty compatible scaling, and damping compatible scaling. They also make plain where the program remains incomplete: the source law, the detailed response kernels, the emergence of universality within experimental bounds, and the eventual requirement of a measurable departure from standard GR plus QED. My heat bath analogy is not merely rhetorical. There is substantial literature showing that gravitational field equations can be regarded as thermodynamic or equation of state statements under suitable conditions. Jacobson's derivation of the Einstein equation from delta Q equals TdS is the cleanest benchmark, and later entropic or emergent pictures of gravity extend the same broad lesson. Macroscopic gravitational behavior may encode underlying microscopic degrees of freedom rather than exhaust them. This does not prove my model. It does, however, justify the style of explanation. If Einstein's equations can emerge as an equation of state, then it is reasonable to search for a deeper matter and environment description whose coarse-grained limit looks geometrical. My program belongs in that family of thought. Its distinctive claim is that the relevant coarse graining may be written in terms of oscillator equilibrium, available driving power, and a real stochastic field environment that changes the scale of matter itself, while geometry serves as the macroscopic encoding of those changes. I also want that thermodynamic analogy stated carefully. I am not claiming that spacetime is literally a fluid or that thermodynamic language proves my microscopic picture. The point is narrower. If Einstein's equations can appear as an equation of state, then the metric may be a coarse-grained description of deeper degrees of freedom rather than the final ontology. That is the sense in which I use thermodynamics here. This also connects naturally to the vacuum equilibrium strand of my own work. Puthoff's equilibrium description of radiationless ground states, together with the earlier harmonic equilibrium picture in which particle scale is set by balance with a structured vacuum spectrum, suggests a common theme. Matter properties may reflect a stable balance between internal dynamics and a surrounding field environment. My use of K and zeta can therefore be read as state variables of a matter-environment system, while geometry records the macroscopic comparison rules that emerge from it. Stated this way, the thermodynamic analogy motivates the present model without overclaiming. It tells me why an operational, matter-centered reinterpretation of GR is reasonable to pursue. It does not yet tell me the final microscopic field theory. For a static spherical source with negligible net charge, I adopt the identification zeta squared of r equals 2 gm over c naught squared r. In that case, k of r equals 1 over 1 minus 2 gm over c naught squared r, and the operational relations reproduce the standard weak field scalings of redshift and coordinate light speed in the chosen convention. At the surface of the Earth, one obtains zeta of Earth of approximately 3.73 times 10 to the negative 5, and a corresponding normalized frequency shift of order 10 to the negative 9, consistent with the fact that small fractional shifts can encode large macroscopic accelerations. This is an important engineering point. The model does not require large changes in dimensionless spectral quantities to produce the gravitational environment familiar in ordinary life. That observation, already present in my earlier papers, explains why the control problem is hard. Even if the target shift is dimensionless and small per constituent, the total energy bookkeeping for macroscopic matter can still be enormous. The small signal metrology relation follows directly from the scaling table. Since frequency divided by reference frequency equals k to the negative 1/2, which also equals the square root of 1 minus zeta squared, a small engineered perturbation around k approximately equal to 1 gives a fractional frequency shift approximately equal to negative 1/2 delta k over k, and also approximately equal to negative 1/2 delta zeta squared. This is the practical equation to keep in mind when translating the model into a clock or spectroscopy experiment. This matters because modern optical clocks already operate in the 10 to the negative 18 regime and have resolved relativistic redshift effects over laboratory scale vertical separations. That does not validate my model by itself. It means only that the metrology is already sensitive enough to make a controlled search for a K-like perturbation a meaningful engineering question, if such a perturbation can be generated cleanly. The experimental language also benefits from sharpening. NMR and EPR are not Compton frequency technologies, and I do not claim otherwise. The cleaner statement is that low-frequency laboratory probes may act as control interfaces into a much broader environmental coupling kernel. They can perturb state populations, coherence times, line widths, relaxation channels, and possibly the effective damping parameter, without themselves being identified with the highest frequency content of the ambient bath. That distinction suggests a realistic experimental program. I would not begin by claiming artificial gravity. I would begin by searching for anomalous geometry like frequency shifts or clock comparison effects that remain after ordinary Zeeman, Stark, Lamb cavity thermal and mechanical systematics have been removed. The targets are precision spectroscopy resonators with tunable quality factor, atomic and solid state clocks in engineered electromagnetic environments, and materials whose internal relaxation channels can be modulated reproducibly. Any positive claim must be differential, repeatable, and demonstrably larger than standard electromagnetic back action. The resonance program is therefore a probe of coupling, not a proof of any active non equilibrium engineering application. If an anomaly were found, it would still need to be mapped back into the K table, checked for universality across materials, and tested against equivalence principal bounds. The first discriminant is universality. A genuine K-like effect should shift distinct transitions by the same fractional amount when those transitions are exposed to the same engineered environment, because the hypothesis concerns the local scale of the clock sector itself. By contrast, ordinary Zeeman, Stark, and Lamb type shifts carry species and transition dependent coefficients. The second discriminant is the geometry of comparison. Because a universal K-like perturbation rescales the local clock sector, two dissimilar clocks placed inside the same engineered region may preserve their ratio to leading order. The more decisive observable is comparison between a clock inside the engineered environment and an external reference, or between two regions whose loading protocols differ in a controlled way. The third discriminant is protocol. Because the hypothesis concerns damping and loading, not merely static field amplitude, the most informative searches modulate cavity Q, line width, relaxation pathways, or spectral loading, while conventional field amplitudes are held as fixed as possible. The signal to look for is a residual geometry like shift that tracks the loading protocol rather than the ordinary electromagnetic coefficients alone. The present paper establishes the passive branch of the model, with zeta greater than or equal to 0 and less than 1, and k equal to 1 over 1 minus zeta squared. The operational map implies k greater than or equal to 1. This is the branch that reproduces ordinary gravitational slowing of clocks, contraction of lengths, and the static and weak field matching developed in the preceding sections. It is the branch for which the source law and damping identification have actually been written here. That scope matters. The closures adopted in this paper are phenomenological weak field constructions, not yet a completed strong field theory. Their purpose is to recover the observed static gravitational relations and to define a disciplined metrology program for spectroscopy, clock comparison, and resonance-based perturbation studies. The natural boundary of the present branch is zeta approaching 1 from below, for which k approaches infinity. How the model should be continued through horizons or replaced by a more complete microscopic theory in strong fields remains future work. For the same reason, I do not advance any k less than one engineering claim in this paper. A driven or active non-equilibrium regime with k less than 1 would require a different control law, a separate derivation, and a demonstration that the effect is not ordinary electromagnetic back action dressed up in new language. The present paper therefore keeps its focus on the ordinary branch, the operational reinterpretation of GR within that branch, and the search for small anomalous K-like shifts in precision systems. The virtue of the present synthesis is that it preserves the conceptual core of my work while stating it in cleaner and more rigorous terms. I am not claiming that all of quantum gravity has been solved. I am claiming that a non geometrical interpretation of gravitational observables can be written coherently. that the uncertainty products can be preserved exactly under the adopted scaling, that the damping model reproduces the same transformation table once the identification k equals 1 over 1 minus zeta squared is made, and that the same weak and static observables of GR can therefore be read through a different ontology. That point deserves to be said plainly. In the regime treated here, my model is not offered as a rival set of weak field predictions to general relativity. It is a reinterpretation of the same successful relations. Wherever the same field equations and scaling laws are recovered, the physical predictions are identical. What differs is what those equations are taken to mean. On this operational reading, Einstein's equation is not first treated as proof that a spacetime manifold is the fundamental substrate of reality. It is treated as a compact tensor map relating the observed relational structure of clocks, rulers, signals, and motion to the matter-energy content of the fields from which those standards of observation are themselves built. This does not diminish the mathematics of GR, it reorders the explanatory priority, while the geometrical interpretation has enriched the mathematics of gravitation enormously. Its ontological primacy may also have constrained the search for quantum gravity by encouraging us to quantize geometry first and ask operational questions later. My claim is not that geometry is useless, but that it may be macroscopic bookkeeping rather than microscopic cause. The burdens that remain are clear. First, the environmental field variable requires a proper source law. Second, the relation between the spectral environment and the damping variable must ultimately be derived rather than phenomenologically weighted. Third, the universality of free fall must emerge or be explained within experimental bounds. Fourth, the model must predict a measurable deviation from standard GR plus QED if it is to move from interpretation to testable theory. Fifth, a full strong field completion lies beyond the weak and static branch developed here. None of those are small tasks, but they are the right tasks, and stating them plainly is part of what turns a speculative idea into a research program. The work assembled here shows that my program has a coherent and defensible core. The observed weak and static effects of gravitation may be written operationally through a single scalar variable k. The same table can be made fully compatible with the Heisenberg products by assigning the complementary momentum and energy scalings appropriately. The same table can then be matched again by a damped oscillator description through the identification k equals 1 over 1 minus zeta squared. In that sense, my long-standing claim survives careful scrutiny. There exists an engineering reinterpretation of gravitational scaling in which clocks, rulers, energies, and frequencies change because matter is operating at a different equilibrium scale, while geometry serves as the macroscopic encoding of those changes. My claim, then, is not that general relativity has been overthrown, but that its equations admit a disciplined operational reading that is at least as natural for engineering purposes as the standard geometrical one. In the regime treated here, the model is intended to recover the same physical predictions as GR because it is a reinterpretation of those same relations. What changes is the ontology. The metric is read as a comparative map of physical clocks, rulers, signals, and energies, rather than as direct evidence that a spacetime manifold must itself be the fundamental ontology. This paper has also clarified what must be said more precisely than before. The controlling field is treated as a real effective stochastic background variable whose spectral and stochastic descriptions refer to the same underlying vacuum environment at different levels of description. Thermodynamic analogies motivate the search for an underlying layer, but do not prove it. NMR and EPR are best understood as control probes of coupling, not as direct access to Compton scale carriers. Any active K less than one extension lies outside the passive branch developed here and is not advanced in this paper. Even with those cautions, I regard the interpretive model as valuable. It places the emphasis where an engineer naturally wants it, on what clocks do, what rulers do, how matter is scaled, where the power flows, and which parameters one would have to control in order to move from observation toward technology. If a deeper, non geometrical account of gravitation is ever found, it will have to recover the same observational table. My claim is that the framework developed here is one disciplined way to begin that search. Let the observed coordinate comparison be length contraction by 1 over square root of k and clock slowing by square root of k. Then choose the complementary uncertainty scaling so that momentum scales by square root of k and energy scales by 1 over square root of k. Direct multiplication preserves the Heisenberg products. Thus, the adopted gravitational comparison table is compatible with the standard Heisenberg products without modifying the uncertainty principle itself. The engineering model introduced here uses a phenomenological damping factor zeta, for which the frequency and energy scales are multiplied by the square root of 1 minus zeta squared, while time scales by its reciprocal. Defining k as 1 over 1 minus zeta squared gives the matching immediately. Every row of the unified scaling map then follows by direct substitution. For the static spherical matching used here, set zeta squared of r equal to 2gm over c naught squared r. Expanding for weak field where 2gm over c naught squared r is much less than 1 gives the expected leading order potential dependence in the chosen
Simplest closure that preserves the present interpretive program is to identify the damping variable with a weak field potential in the same way the Newtonian potential appears in the leading order Schwarzschild and polarizable vacuum map. I therefore take the effective source density to include both ordinary matter and the matter-induced departure of the local field environment from the baseline vacuum state. For a static spherical source, the usual potential is recovered and the matching used in the main text follows immediately. This appendix does not pretend that the microscopic source law is finished. It makes explicit the minimal closure already implicit in the weak field matching of the main paper. The environmental field variable is most naturally separated into a spectral state variable and a response variable. A coarse-grained local environmental energy density may be defined by a weighted integral over the effective spectral environment, while the effective damping rate and damping ratio are written phenomenologically. The corresponding local response function of a bound mode then takes the usual damped oscillator form, which shows explicitly how the spectral environment and the damping parameter enter at different conceptual levels. The environment is the bath. Zeta is the scalar summary of the bath's effect on the mode of interest. If the K-map is common to all matter processes, then leading order free fall is universal. Composition dependence may be parameterized by small residual response coefficients. In this framework, the burden is therefore clear. Any material dependence hidden in the response kernels must be suppressed sufficiently that the Eötvös parameter remains below present experimental limits. The final microscope result gives the relevant order of magnitude for that requirement. For a small engineered perturbation about k approximately equal to 1, the metrology equation is immediate from the scaling map. This is the direct bridge between the interpretive model and clock-based experiments. Modern optical clocks and clock comparisons are already sensitive enough to make such a search technically meaningful, provided conventional electromagnetic systematics are controlled to the same level. The passive oscillatory branch developed in this paper is defined by zeta greater than or equal to 0 and less than 1, and by the real frequency identification in which omega sub zeta equals omega naught times the square root of 1 minus zeta squared. If the same spherical damping map is formally continued beyond the weak field regime, then the model supplies a natural strong field boundary of its own.
Define the Schwarzschild radius in the usual way and rewrite the spherical matching in that language. The horizon is then the point at which the underdamped branch reaches zeta equal to 1. In the present comparison scheme, this is also the point at which the external static scaling parameter diverges. Approached from the exterior static branch, the limit from above implies k approaches infinity. In damping language, this is a critical point. For radii below the Schwarzschild radius, the continuation lies on the overdamped branch. Thus, the ordinary real frequency map used in the main text terminates at the critical point and must be replaced inside the formal continuation by a relaxation rate description. I do not present this appendix as a completed interior black hole solution, nor do I claim that a freely falling observer encounters a local singular dissipation at the horizon. The point is narrower. The same damping model used for the passive gravitational branch contains a natural strong field boundary at zeta equal to 1, with an overdamped continuation below the Schwarzschild radius. That observation suggests a path for extending the model beyond the strict weak field regime without altering its operational starting point. If you enjoyed this video, please subscribe, share it, and give it a thumbs up. I look forward to your feedback.